So now we're going to go on to our second presentation of this current session. Our next speaker is Stefan Nikolaj, who is a 19-year-old student from North Macedonia. He's studying at Nova International Schools, and the topic of Stefan's talk is supplementing and interfacing with legacy embedded systems using RT-thread enabled microcontrollers. So over to you, Stefan.
Oh, and can you hear me and see me? Is everything okay?
Yes, everything's perfectly. I'm as smooth as it could be. Thank you so much.
Okay, I'm glad. So, hello, my name is Stefan Nikolaj. I'm a 19-year-old student from North Macedonia. I've been programming and building electronic circuits since I was around 14 years old. I've done freelance work and contributed to multiple open source projects, one of which is, of course, RT-Thread. And I'm here today to talk to you about legacy systems and how to interface with them, giving two examples with RT-Thread and why you should do that if you ever find yourself in a situation where you have to interface with a legacy system, why you should use RT-Thread. So first, I also want to say that I'm very grateful to RT-Thread for focusing so much on the voice of the developers in this conference. In this case, legacy will be defined as a system that is older than approximately 20 years old. So between 20 and 40, even though that is not a hard limit, since those systems are often more loosely coupled and easier to use as well as easier to find. And this topic I find contrasts well with the previous talks, as the previous presentations discussed how you can use RT-Thread in brand new wireless, embedded AI, generative AI, IoT systems, while I'm about to tell you how you can also use RT-Thread to take something old and give it a second life. So I'd like to begin by discussing why you should use an RTOS in this context, then discuss why you would want to reuse and build on top of legacy systems, and then finally show a demo with a recycled PLC, so an old PLC which had its processor module die, how I took the I/O module, connected it to a RT-Thread enabled microcontroller, and made it work again. So this presentation primarily will cater to hobbyist and freelance developers, as that is my area of expertise, but many of the concepts discussed can be applicable to professional projects. Still, it is important to note that I do not recommend repurposing old parts into new projects, into new products, particularly if they are involved with mains electricity or have implications for someone's safety or well-being, and which should safety should always take precedence in these scenarios. So first, let's introduce a pattern observed in the history of technology. So typically, a technology is initially discovered by an individual or a team, and during this initial phase, the technology is in the process of being understood and improved. There are no established standards yet, and often the technology is intended to address a problem that may not even be fully recognized at the time. A prime example of this, which we discussed earlier, is machine learning and AI, which was discovered and understood long ago in the 1970s approximately, but could not be effectively implemented due to the limited computational capabilities of computers at the time. And after this initial period, around 20 years later, the technology undergoes a phase of standardization and begins to experience widespread adoption. A notable illustration of this is the personal computer. Before the emergence of the IBM PC running MS-DOS on an Intel 8088 processor, there were numerous systems that were mutually incompatible. The IBM PC did not introduce any new inventions, nor was it particularly fast or equipped with abundant memory. Its groundbreaking aspect lay in taking an existing concept and establishing a standard, while providing a shared development environment for all programmers. Prior to this, programmers were accustomed to writing separate programs for each system they would develop software on. And I will use this example later to demonstrate how many of the advances made in the embedded field parallel the example of how disruptive the IBM PC was to the desktop computing field. And this pattern is reflected across various technologies including electrical engineering and embedded software development. However, in the embedded world, factors such as higher entry costs, stricter safety standards, and the requirement for long system lifetimes and uptime often result in innovations arriving later. Nevertheless, even with the advent of innovations, legacy equipment remains in existence, albeit often partially non-functional and worn down, since, of course, time takes its toll. And especially in the context of this, I want to mention that a few weeks ago, I saw a 4-bit microcontroller, which was still in use in an industrial factory, still working as it did 40 years ago. So during my visits to many factories, I've observed large stocks of old industrial parts and PLCs that the factories either sell on platforms like eBay, they give to employees, or just throw them away. Conversely, consumer equipment tends to be disposed of or shipped to distant countries and unfortunately ends up in landfills or sometimes in recycling centers. I delved into a detailed exploration of this phenomenon last year, focusing on musical synthesizers, which is also how I got introduced to RT-Thread in last year's RISC-V design challenge. So in this case, synthesizers built in the 1980s and 1990s possess a distinct sound that remains highly coveted today, and that sound is typically attributed to a single integrated circuit which generates all of the sound. Recyclers often disassemble these synthesizers and sell the functioning integrated circuits, which in most cases are still in perfect working conditions online or locally. And these represent an example of legacy systems which are relatively easy to interface with. So in both scenarios, in the PLC and the synthesizer example, these systems, even though they may not be very usable or viable to still produce commercially, they can still be utilized by hobbyists and enthusiasts. However, due to their complexity and their age, they're often overlooked. Still, regardless of this age, these systems were created by teams that likely invested years of effort in development, debugging, and refining their work. And fortunately, the modern era has provided developers with tools that can significantly accelerate software development, with the real-time operating system being one of the most crucial tools in this regard, enabling the solo developer or the small team to become as fast in development as these old themes, which would require much more effort to do the same. So next, I will discuss the primary method by which hobbyists can engage with these legacy systems, which most often involves replacing the processing component with an RT-Thread-enabled microcontroller and utilizing the peripheral component. So the examples provided focus on legacy peripheral elements that are controlled by a modern processor or microcontroller, where peripheral elements are hardware components like sensors, relays, motors, actuators, anything that connects the external world to software. And here is where the key advantage of RT-Thread, or one of the key advantages of RT-Thread, becomes apparent. Software development becomes more straightforward, and the loosely coupled nature between RT-Thread and the underlying physical microcontroller allows for seamless support of various processors using an almost identical code base. So the first step in dealing with legacy systems is establishing the physical connection. And in this section, I will share my experience with reverse engineering and finding information to interface with legacy systems. I'll take the example of this relay board on the picture there, which I took from a discarded from the industrial PLC, which I mentioned in the beginning, whose processor board had failed. The most challenging part of connecting this relay board to the microcontroller was the lack of information about its operations, schematics, and connector pinout. However, because the hardware was relatively simple and the board was connected to a Z80 microprocessor bus, reverse engineering it wasn't too difficult. And this is where my main tip for both this, and I think it could be applied more generally, To understand embedded systems, you need to build embedded systems. And to build embedded systems, you need to understand embedded systems. And one of the best ways that I learned to build and reverse engineer and design was just through curiosity. I would search for open source or free schematics online, try to understand how they would work, and build my own project, noting the challenges that came with the different choices I would make while designing it. For example, this relay board has two series RC filter networks for the relay enable signal. This design choice ensures that stray signals don't accidentally activate the relay board during startup, and only a strong signal from the microprocessor can turn it on. Understanding this choice can only come with experience. And also, another important tip to develop is the skill of examining schematics and components as cohesive units. Because, for instance, let's consider a relay board, which can be divided into three groups of components: the bus interface circuit, the relay drivers, and of course, the relays themselves. All of these groups are logically essential and generally exhibit similarity in most other comparable systems. Most relay drivers are the same, and the ICs used to drive the relays typically adhere to their datasheet circuits, with the only notable exception being the inclusion of a series RC network in this case. If you have experience driving relays with circuits and have previously connected a Z80 multiplex bus, you can readily comprehend the operational principles of this relay board. And in the salvaged PLC boards, for example, it has optocoupler input boards, which also adhere to the same underlying principles. So here in this slide, you will see for schematic analysis, two excellent resources are electrotania.com and archive.org. But you should also strive to just learn from building things and experience. And also another note is the voltage difference and how you can address it. So most microcontrollers supported by RT-Thread operate at 3.3 volt I/O or below. I don't think I've actually seen a microcontroller that supports RT-Thread and has a native 5 volt I/O. But most legacy systems, especially the ones that are 20 years old or older, utilize 5 volt I/O. A simple solution to address this issue is to employ voltage shifters. And for example, you have the TI-TXB series, which has automatic signal direction detection, supports wide range of voltages, or discrete MOSFET level shifters. Both of these types have numerous pre-designed breakout boards available online, so implementation is convenient. So in both of the examples I provided, the synthesizer and the PLC, the peripherals utilize a parallel bus that incorporates signals for chip select and read-write operations. This type of bus is very commonly found in older systems, but is less prevalent in newer ones, which may employ different communication protocols. Usually, you will see in the PLC world things like Ethernet, different Ethernet protocols, Modbus. I've seen CAN, and of course RS-485. Reverse engineering these protocols can be more challenging, but if you have the datasheet, the application notes, and you know the chips present on the board, it's likely that you can find some information online, the communication board in the protocol in the datasheet itself. So as long as you have access to the datasheets for these chips, you can determine the communication protocol, unless you're dealing with a custom programmed slave microcontroller. In that case, you could use a logic sniffer or an oscilloscope, but this does make it harder. However, RT-Thread does offer built-in support if you're dealing with protocols like UART, SPI, or I2C through its host-independent subsystem. So when dealing with older PLCs, they very, very often use RS-485. And this can be really easily managed if you use an RS-485 transceiver IC combined with a UART subsystem. And moreover, the pin device framework allows for independent control of a parallel bus from the host microcontroller. So as long as your microcontroller is fast enough to monitor and control the parallel bus, you can use any microcontroller that supports RT-thread, even a microprocessor, connect it to the parallel bus, and it will work. It will drive that parallel bus perfectly, and the peripheral will not know whether it's an original processor or a microcontroller. And generally, microcontrollers supported by RT-thread possess adequate speed to fulfill the communication needs in these legacy environments. So for establishing the physical connection to these systems in a platform-agnostic RT-thread manner, the official documentation contains all the necessary information. It's great, and I'm not just saying that because I wrote part. By referring to the documentation, you can effectively control and manage the physical connections to these systems. But now that we have the physical hardware side, let me also talk about the advantage of using RT-thread and just in general more modern design principles. So these are three boards these are the three main processing boards in the PLC. It consists of 6 I/O boards and these 3 processing boards, of which one is the microprocessor board, one is the communications board, and the third is the ADC board. Even though the total number of ICs is quite extensive, this PLC dates from only 2004, even though the design does look like it's older. And nowadays, though, a single microcontroller running RT-thread can replace all of these 3 processing boards and offer enhanced functionality at a lower cost while occupying significantly less board space. So in the case of this PLC, I think it ran some variant of CP/M, the Z80 operating system CP/M, and using RT-thread, well, RT-thread does appear to be better in every single way from this old operating system while still being an operating system and having the same advantages and even more. And this transformative streamlining, as highlighted earlier with the example of the IBM PC, is reflected in the advantage of employing RT-thread over writing bare metal code. In essence, the introduction of desktop operating systems brought comparable benefits to the desktop space as real-time operating systems brought to the microcontroller space. And I believe that RT-thread stands out in this context due to its support for popular microcontrollers and its accessibility as a free and open source platform. So to provide a clearer contrast, let me delve into the original configurations of the PLC and the synthesizer. So the synthesizer featured a microprocessor with a RAM IC, a ROM IC, bus decode circuitry, and the peripheral chip responsible for handling the incoming UART signals. This arrangement results in high system costs, increased size, and higher programming complexity. Modifying even a single component within the entire system would be very challenging. Moreover, the ROM contained a single program running in a super loop, making it difficult to introduce changes or add new functionalities without extensively modifying the entire program. Additionally, altering the main microprocessor itself would be a daunting task as the system was programmed in assembly language, requiring a complete rewriting of the entire program for if the microprocessor was changed, or even within the same microprocessor family. And the PLC faces a similar challenge as both the PLC itself and the main bus are designed around the specifications of the Z80 processor. So modifying components within the system necessitates changing the main microprocessor, resulting in a significant redesign. And this underscores the clear advantage, one of the clear advantages, as outlined in this slide, offered by RT-thread, where platform agnostic development using a programming language like C or C++ is highly preferable over the bare metal approach and super loop structure characteristic of legacy systems. And the flexibility and adaptability of RT-thread enable easier modifications and enhancements to the system without the need for extensive redesign or rewriting of the entire program. So While many hobbyists and novice developers may have experience primarily with superloop programming, getting started with RT-Thread is straightforward, especially in this context. So it proves to be advantageous for individuals who prefer software development over hardware constructions, and also people who may have budget constraints preventing them from purchasing a specialized development kit or a new PLC, as as shown in the example, since this is an old PLC I'm using, which has essentially all of the functionalities of a new one, except that I'm reusing something that already exists and works really well. Although it is possible to accomplish tasks solely within a superloop structure, which is how legacy systems are mostly originally designed, I will highlight several aspects where RT-Thread, for me, significantly simplified the process. So, of course, modularity is a crucial aspect, particularly for hobbyists and novice developers, in my opinion. As code bases grow, they can quickly become overwhelming and difficult to comprehend. Many developers can relate to the experience of returning to a code base after some time and feeling lost in understanding its workings. In the case of building a PLC or a synthesizer, these projects are ideal candidates for modularity due to the non-high speed and low speed nature of their peripherals, who are also quite loosely coupled. Modularity also facilitates team collaboration by allowing task delegation and introducing an additional layer of abstraction in the form of drivers. So this modular approach also brings embedded software development closer to a desktop environment, which proves highly beneficial in most cases. And furthermore, modularity offers the advantage of scalability and code reuse, significantly simplifying future development efforts. Real-time behavior is also a fundamental aspect of real-time operating system. I mean, it's in the name, and it's precisely this characteristic that makes them well suited for embedded environments. In the context of a PLC, for instance, precise timing is essential for time-critical components. And in the case of a synthesizer, you can actually feel the delay, because the main criticism of desktop computer emulated synthesizers is in the delay. Even a slight delay of 10 to 20 milliseconds can cause significant issues for musicians. So having an operating system like RT-Thread, which has a few microseconds, I think in a previous presentation it was discussed, between 1 and 3 microseconds of interrupt delay time, ensures accurate and timely execution of tasks and eliminates undesirable delays, providing necessary real-time performance required in such applications. And finally, one third important feature of real-time operating systems, task prioritization and interrupt handling. So you program an interrupt from a circuit which signals that your PLC is on fire and you need to shut down everything or else the building will burn down. And the interrupt is then interrupted by an unrelated ISR. Maybe the UART circuit received the message. Your saved building routine is now interrupted. It can happen, since I've seen developers never test the routines, which are supposed to happen once in a lifetime, but shouldn't. And this is made worse if you're using a super loop, where usually for many microcontrollers, you can only have one interrupt going on at a time. And doing that in software, as RT-Thread does, is much nicer. And finally, I want to talk a bit about interfacing the PLC relay board. So this is an older image using an Arduino, but what I want to show here is how my prior knowledge of the system's architecture and the use of a Z80 processor enabled me to identify the presence of a multiplex Z80 bus. So I'm just going to discuss how I reverse engineered this and how I knew how and what to replace with an RT-Thread microcontroller. So understanding the specific signals associated with this bus, such as the chip select, write signals, byte selection, was essential for successful reverse engineering. And this serves as a valuable tip when approaching these reverse engineering tasks. If you have a clear understanding of the expected signals and operational methods, you can recreate that. Well, you can recreate that in a tiny fraction of the time it took the original developers to do so. And so, for example, working with the relays was, for me, was really straightforward because the driver only needed to manage the bus and control the 3 designated signals, and RT-Thread gave me all the tools I needed to do so. For the synthesizer, with which I entered in last year's RISC-V Design Challenge, I had the datasheet of the chip used, built my circuit around it, and the hardware connection was straightforward. And the software side, it was difficult, but it was very functional and modular, and it was made much easier than if had I programmed it in a super loop structure, because I was able to write separate screen driver, button scan, potentiometer access, and have it in a platform agnostic package. And the main idea was to be able to use multiple synthesizers at the same time, so multiple chips simultaneously, which I was able to do so. And all of the ICs in that project, apart from the microcontroller board and the display, were recycled from past synthesizers. So this project gives you an environmentally friendly synthesizer too. And in conclusion, RT-Thread offers a very compelling solution for interfacing with legacy systems. It's platform agnostic development environment. It's built-in support for communication protocols, both simplify the integration process, making it accessible to both hobbyists, freelance developers, and of course, larger teams. And this emphasis on modularity enhances code organization and eases collaboration, while the real-time behavior ensures accurate and responsive performance in time-critical applications. So with RT-Thread, developers can breathe life into legacy systems, unleashing their full potential and transforming them into modern and efficient solutions. So if we have time now, I have a small demonstration prepared for the system itself. Can you give the account Stefan Nikolaj demo permission to share? In the meantime, I'll set everything up. It's just a short demo showing that indeed this PLC system, this DIY PLC can actually work and do all of the tasks a real original PLC could, but with a fraction of the development time and complexity for now. And I found that these legacy systems just seem to work forever. They just work. For example, the 4-bit microcontroller. Here we're talking about 32 and even 64-bit microprocessors, microcontrollers. And I saw a 4-bit microcontroller handling a massive hundreds of thousands of kilowatts industrial furnace.
Yeah.
So
the other thing is, if you've got something and it works, don't change it
until it breaks.
Well, so, yeah, that's the downside. When it breaks, whoever created it is no longer with the company, and no one knows how it works.
Or since I am in North Macedonia, I've seen the companies that made them just not exist anymore for decades. The country they were made in does not exist anymore. So
I was talking to a company who's doing some software, and they told me that a lot of the software in the internet, we're now used to using high-level tools that use libraries, that call libraries, and some of the lower-level libraries are so far down that no one knows, what's in them anymore, almost, which is scary. Okay, we can see your screen now.
Okay, excellent. So this is the PLC board. This is just a simple breadboard with some LEDs, and I will just have this relay just cycle a pattern. So maybe, I don't know if you can see yes. So these relays are switching, and it works instantaneously, much faster than the original system. And unlike the original processor board, this works. And this proof of concept, I was able to build quickly. I planned to include more features, but unfortunately, it seems like I've ran out of displays and buttons. So
now people are saying that they can only see me, but I can see your screen, which seems very strange. Oh no, and somebody else say that they can see the demonstration.
Yeah, no, I turned off my webcam. So, but yes, that was.
Oh, now that it's yeah, now we're seeing.
Yeah, so that was the presentation, and thank you for your attention. I hope you found the information valuable and insightful.